All right, I'd like to welcome all of you to the Smithsonian National Air and Space Museum and to the Moving Beyond Earth Gallery. Today we have our What's New in Aerospace program, sewing machines, balloons, and rocket fuel. And our program today is sponsored by Boeing. I'd like to welcome all of our online viewers and our folks from NASA TV, as well as those of you in the audience today. Our speaker today is Dr. Ian Clark. Dr. Clark is the principal investigator for the Low-Density Supersonic Decelerator Project. In 2012, Clark received the Presidential Early Career Award for exceptional leadership and achievement from President Obama. At the end of his presentation, we'll have an opportunity to take questions from the audience as well as our online viewers. So let's give a round of applause to Dr. Ian Clark.
Thank you, Mark, and thank you to the Air and Space Museum for inviting me today to give this talk, and thank you all for attending. The title of my talk is called Sewing Machines, Balloons, and Rocket Fuel, and you're probably wondering what these three very disparate objects have to do with the future of Mars exploration, in particular, how we land on Mars. So my talk will give you a little bit of an overview of technologies that we're developing here within NASA this year and last year and over the past few years, that we use for landing our missions on the surface of Mars. But we are, of course, at the world's coolest museum, so I'm actually going to start off the talk with giving you a little bit of history about how we've developed the technologies and how we currently land on Mars today. So let's get started. This is the Curiosity rover, or sometimes known as the Mars Science Laboratory. It's a little less than a full metric ton. It's about the size of a small SUV. For comparison, it's about twice as heavy as the Mars lander, Viking lander prototype that's just outside this exhibit gallery. You guys can take a look when I'm done. But at 900 kilograms, it is the largest, most massive thing that we've ever landed on another planet. It's six-wheel drive, nuclear-powered, laser-equipped, and putting it safely on the surface of Mars was a tremendous engineering challenge. So how did we do that? Well, we start at the top of the atmosphere, the Martian atmosphere, encapsulating the rover inside a very large blunt body. It's about 15 feet in diameter, and it comes screaming into the Martian atmosphere at about 10,000 miles an hour. We use the atmosphere to help slow down from about 10,000 miles an hour down to about 2,000 miles an hour, where we hit the emergency brake. We deploy a large 65-foot diameter parachute at over twice the speed of sound. That slows the capsule down from 2,000 miles an hour down to about 200 miles an hour, at which point we have to turn on our rocket engines. We use something called the sky crane system to help slow it down a little bit further and gently bring the rover closer and closer towards the surface of Earth, bring the velocity down to zero, and then slowly lower the rover down to the surface of Earth. The wheels deploy, hit the surface, we cut the cables, the sky crane flies off in the distance, crashes in the distance, but the rover is there, safely landed, and today it's doing amazing science for us. How we've landed things on Mars hasn't really changed a whole lot in the past 40 years. We start at the top of the atmosphere with very large vehicles that we use to help slow down, but those aren't adequate enough. We have to use parachutes that are deployed at several times the speed of sound to slow us a little bit further, and we use rocket fuel to help slow us to last a little bit and put the payload safely there. We have made some advances, particularly on the blunt bodies. We can actually steer these barn doors through the thin Martian atmosphere to try to get a little bit more altitude and land heavier payloads, some slightly heavier payloads, and also help improve some of the accuracy of where we can land these payloads on Mars. On the landing side, we've improved some of our landing technologies. We've gone from the pulse thrusters that the Viking lander, like the one outside, used, to airbags that we've used for some of our smaller rovers, to more recently the sky crane system. But one of the areas that we haven't really made any significant advancements in are these supersonic parachutes. They're still the cornerstone of our supersonic decelerators that we use for our Mars missions. Now, we want to land things that are a little bit bigger, and this is the part where if you guys could sort of grab onto the side of your chair and hold tight, because we're about to do some math. How we slow down, there's two main things. For as long as we've been accelerating and sending things into space, we've been trying to figure out how to slow them down safely. We can either use rocket fuel, tends to be very heavy, not particularly efficient, or we try to use the atmosphere to slow us down. And the way we use that is we generate drag. And how do we generate drag? Well, that's the equation up here at the top. There's four components to generating drag. the density of the atmosphere, the fluid that I'm traveling through, the velocity of which I'm traveling through that fluid or through the atmosphere, something called the drag coefficient. It's the measure of the efficiency or inefficiency of the shape of the device, and the size of the device, the area. If I take our force of drag and I couple that with Newton's well-known second law here, F equals ma, force equals mass times acceleration, I have that the deceleration due to drag is equal to this. And there's these two terms over here, the size of the object and the mass. And those are the things that tend to change the most every time we try to send another probe or spacecraft to Mars. So if we think about as we grow larger, the length of the size of the thing grows. Well, the area is only going to go roughly with the square of the length. But the volume will go with the cube of length. And since we tend to be very efficient at stuffing as much things as we can in whatever volume we have available, that means that the mass of the object will go with the cube of the length. So if I look at that acceleration and I put the ratio of the size in terms of area to mass, I get A over M, I get 1 over L. That means that as L gets bigger, as the objects get bigger, as the rovers get bigger, it becomes harder and harder to slow them down. And that's one of the challenges that we face today. But it's not a unique challenge. It's actually a challenge similar to one that we had 40 years ago. Think back to 1962. NASA's in its infancy. NASA's beginning to develop the Saturn V, the largest launch vehicle, largest rocket ever built, and the one that we would be used to send astronauts to the surface of the moon, capable of putting over 100 tons in low Earth orbit. Now, at that time, NASA was planning to use that largest rocket ever built to send a probe, the first probe, to the surface of Mars. We had very little knowledge about what Mars was like, but we knew that we wanted to send something very, very massive to Mars. And so in this vacuum of knowledge, we began, in its infancy, to send spacecraft flying by Mars. We began learning more about the Martian atmosphere. We had observations from Earth that we could make to try to understand how thick the atmosphere was, but it wasn't really until we started doing these flybys of Mars that we began to getting a better insight into the Martian atmosphere. So this figure here, this plot, gives you a little bit of history of our understanding. It's density versus altitude at Mars. And so for comparison, I've put what sea level density here at Earth is. About 1.225 kilograms per cubic meter is the density of our Earth's atmosphere. If we look back in 1964, they thought the Martian atmosphere near the surface was maybe a fraction of that. Call it 1/10 or so, maybe 7% of Earth's density. But as we started learning more and more, that number got smaller and smaller. Our knowledge of the Martian atmosphere, particularly at the altitudes where we do most of our deceleration, started indicating that the Martian atmosphere was very, very thin. And today we know that the Martian atmosphere is actually only about 1% the thickness of Earth's atmosphere. So if you think back to that equation that I showed you where drag has that rho, that density variable in there, you realize that to generate drag, you don't really have a whole lot of density to work with, so you need very, very large objects to help create that drag to slow you down. So in that vacuum of technology of the early 1960s about how to land on Mars, we started developing all kinds of things. Inflatable devices that would be stowed on the back of an aeroshell that we can inflate at 4 times the speed of sound to grow the size of the aeroshell, to create more area, to create more drag, to help slow them down. Things that would be ram air inflated with these little scoops on the side. For the first time, we started taking parachutes, things that we had been using reliably for the decades previously. People would routinely jump out of airplanes using cotton or nylon parachutes or polyester parachutes, and they worked wonderfully. We started pushing them into faster and faster speed regimes. Started seeing if parachutes would work at several times the speed of sound. Starting to get our first understanding of what that was like. Some of the very first tests, all occurring in the 1960s. In fact, when we did some of those early tests, we began to see that parachutes operating in a supersonic regime was an entirely different animal than what we were used to. They tended to inflate extremely quickly, less than a fraction of a second, 0.3 to 0.5 seconds. And they were very, very violent in their inflation. Once they got open, they tended to collapse and expand and collapse and expand. And they generated a decent amount of drag, but once they slowed down enough, then they were just like parachutes that we were used to at low Earth altitudes. They provided excellent drag for us. So we started pushing further and further, faster and faster, and we started understanding some of the limits of parachutes. We went to several times the speed of sound, and we began to see where parachutes began beating themselves to pieces or melting because of the high Mach numbers, the aerothermodynamic heating, melting the very thin polyester material that the parachutes were made from. All of that would eventually go away once the Voyager project, which was going to be using that Saturn V rocket, would eventually go away, and in its place came the Viking lander, something much smaller, still relatively large. Again, you can go outside and see. But some of the technologies that were being developed for that program, the Voyager program, weren't going to be necessary. Viking ultimately selected a parachute as being adequate to land those twin landers in 1976. So that off-ramp from all of that technology development that occurred in the 1960s, we took the parachutes and we've used them for every successful Mars mission since. So the Viking landers, of course, in the 1970s, Mars Pathfinder, the Mars Exploration Rover, Spirit and Opportunity, the Phoenix lander, Mars Science Laboratory, the Curiosity, and in the coming years, the Mars Insight lander and the Mars 2020 rover. Some of the other technologies that were being developed would find off-ramps in other areas. We would use them for stabilization devices on the ejection seats for the Gemini capsules. We would use them for stabilization for meteorological sounding rockets that we would send high in the atmosphere to try to understand what the atmosphere was like at altitudes well above what an aircraft can operate at. We'd use them for stabilization and munitions. But ultimately, all of that technology development sort of died down as the applications and the needs for these technologies went away. And it wasn't really until a few years ago that we started having to go back to that. And it was because we were in the same situation that we were in the 1960s. We want to land even larger things on the surface of Mars, and we need technologies with which to do that. As we look to the future of Mars missions, we start thinking about robotic missions, ones that we would use to go and collect rocks on the surface of Mars or soil samples that we could ultimately bring back to Earth for better analysis. Perhaps demonstrations that we'd want to send to the surface of Mars to show that we could take the carbon dioxide of the Martian atmosphere and distill it to make rocket fuel that we could use. Perhaps to land a greenhouse on the surface of Mars to see if we could grow plants in the Martian environment. And ultimately, of course, as we cast our eyes to the horizon, we start thinking about that we want to put humans on the surface of Mars. That's going to be an endeavor that takes the 1-ton Curiosity mass and has to increase it by at least an order of magnitude. You're looking at putting not just 1 ton or 10 tons, but probably closer to 20, 30, or 40 tons. Think Mark Watney and all the different things that he had to have to exist on the surface of Mars, right? His computers, his iPads, iPhones, food, water, whatever's necessary to exist on the surface of Mars for days, weeks, or months at a time. So that's where the project that I'm working on comes into play, low-density supersonic decelerator. We're trying to develop the next generation of supersonic decelerators for use at Mars for landing those future Mars missions. So there's 3 main decelerator types that we're developing. The first off is an inflatable drag device. We call these supersonic inflatable aerodynamic decelerators, or SIADs, because we love our acronyms. This is the first time that we've really developed something of this scale. And so when we were going down this path, we wanted something that we thought we could control and that we could understand relatively well. We wanted a shape that we thought was very deterministic, that we could help control with pressure. We wanted to be able to control the pressure in the inside of the device using gas generators, like automotive gas generators. In fact, the ones that we used for this development testing were precisely like the ones that are behind the steering wheel in your car. We didn't go to a junkyard and rip them out, but they are identical to the ones that are in your steering wheel. So this is a device that grows the size of the aeroshell from about 15 feet in diameter to about 20 feet in diameter. Again, bigger area, more drag generated. And it does it at several times the speed of sound, about Mach 4, Mach 5 or so. It's designed to be a very closed pressure vessel, moderate pressure, about 3 to 4 psi internal, so not a whole lot, but you don't really need a whole lot to maintain a very rigid, defined shape. And it's a device that allows us to gain confidence that when we do things like our wind tunnel testing, or when we develop small models that we shoot out of a cannon to see how they fly, that the results from those tests are scalable to things that are orders of magnitude larger. So we can go from, say, 2 inches in diameter to 20 feet in diameter and feel comfortable that the performance of the device is scalable, that we'll understand how to scale it. Of course, we want to land even larger things, and so we're developing even larger inflatable decelerators. And so there's another device that actually harkens back to some of the devices that were being developed in the 1960s. This one's called an attached isotensinoid. It's even bigger. It's about 27, almost 30 feet in diameter. And instead of having an internal pressurization system, we actually use ram air inlets on the side. This is a picture of one of our engineers standing in front of an inflated version of it. It's upside down. These are little ram air scoops. In fact, to get this thing pressurized to, in this case, it's about 3/4 of a PSI, we had to use 27 bounce house blowers that we supercharged 3 at a time. So we took the exhaust from one, pumped it into the inlet of another, and then took the exhaust of that guy, pumped it into the inlet of another, so we could get enough pressure buildup to get this thing going. So 27 of those got that thing up to a little less than a PSI, but it took full shape, full geometry. So it doesn't take a whole lot of pressure to get this guy up to full shape. And lastly, we're developing a new supersonic parachute, one that's about 2.5 times the size of any parachute that we've ever used successfully at several times the speed of sound previously. To show some comparison, the Phoenix lander of a few years ago, that parachute was a little less than 12 meters in diameter. The Viking was about 16 meters. MSL, the largest supersonic parachute we've ever used, at 21.5 meters. And then here's the parachute that LDSD is developing, about 100 feet in diameter, or the full size of the deceleration system is about that of a Boeing 747-400. Sewing machines. So all of these devices that we're developing are textile devices. They're soft goods. They're made from fabrics or materials that are either woven or braided together. And so we have to assemble them. We have to stitch them either by hand or more commonly using sewing machines. So I'm not really sure that Elias Howe or Isaac Singer really understood the fathom of what they were developing, and that their inventions would become critical for the future of space exploration, but that very much is the case. These lightweight fabrics that allow us to pack them into very small volumes and stow them very easily really rely on our ability to stitch and sew things together. But of course, once we've developed the technologies, we have to test them. We want to make sure that the technologies work the way that they need to, that they have the performance that they have to have in order to use them at Mars, and we want to make sure that they survive the harsh Martian entry environment. And that was one of the biggest challenges of this entire project. Not so much, although it was difficult to come up with the technologies, the fabrication of the technologies is challenging, but we had to figure out ways in which to test them, to stress them, to put them through the environment that they would see at Mars. So when we first started out, we started looking around the country for avenues or venues that we could do this, wind tunnels that we could put them in, vacuum chambers that we could test them in. And we started to realize that none of the vacuum chambers or wind tunnels were big enough, that the energies, that the sizes, the scales of the devices that we were developing and the environments with which we'd have to expose them, that there was no existing way to test them. And that was somewhat of a foundational moment, because if you think back, right, we've been exploring space for about 5 decades now, right? We've gone to every planet or flown by every planet in the solar system. We've landed things on Mars, on Venus, on moons of Saturn. We've sent probes into the atmosphere of Jupiter. And in that time, we've developed all of this infrastructure, things like wind tunnels that are the size of city blocks that use more power than a nuclear aircraft carrier, vacuum chambers that are nearly as large, buildings that were, for a time, the vehicle assembly building, for example, at Kennedy, the largest building in the world. And all of that infrastructure, we've essentially outgrown when it came time to develop these technologies. We couldn't fit our devices in wind tunnels anymore. The biggest in the world is the 80 by 120 up at NASA Ames Research Center outside San Francisco. If we tried to put our parachute in there, it would take up the entire test section. You couldn't even get the wind going. When we started looking at other alternatives, they didn't exist. So we had to come up with our own way of doing testing. So we do lots of that. For the SIAD, for that inflatable drag device, we wanted to make sure that it would survive the stresses and the aerodynamic loads that it would see if it were entering the Martian atmosphere. So we scoured the country, couldn't find anything, and eventually we went out to our friends, the Navy, who operate a facility, the China Lake Naval Air Weapons Station, about 2.5 hours northeast of Los Angeles. They have a 4-mile-long railroad track, standard gauge railroad track, and they let us, with their help, build essentially a 30-foot tall siege tower. It's 40 tons of welded steel that sit on top of 2 standard gauge railroads. We put a mock aeroshell on the front of it. We pack the side to the periphery of that aeroshell like it would be stowed on a Martian entry vehicle. And then we take 6 solid rocket motors and we strap them to the back of it. These are Nike solid rocket motors. These were originally built in the 1950s, and they would be staged around cities like Los Angeles or San Francisco to shoot down Soviet bombers if they ever came our way. Well, fortunately they didn't, and so we've got a bunch of these things sitting out in the bunker in the desert. Relatively cheap and economical to use, so we take half a dozen at a time. We light them off. We go from 0 to 300 miles an hour in 2 seconds, And at those speeds, we're able to replicate the aerodynamic loading that the device would see if we were to enter the Martian atmosphere. So what does that look like? Well, we take lots of video in high definition and slow motion, and we watch the thing inflate. We see how it emerges. We have little dots on it that we use photogrammetry techniques to measure the shape and see how much the shape deforms over time, see how it emerges, and then we see if the shape, if the inflatable device is rigid at these high aerodynamic loads. We did this several times and we saw it work extremely well. In fact, the deflection of this device was on the order of a few centimeters, less than an inch. For comparison, that's about half as much as the rigid heat shield was for the Curiosity lander that we, the Curiosity rover that we landed on the surface of Mars a few years ago. There's the rockets part of my 3 items. But of course, we also wanted to test the parachute. We're developing a new supersonic parachute. So one of the first things we did was try to figure out what does that parachute need to look like? What's the shape? What's the geometry? Where do we put holes? Where do we not put holes? So we did go to that wind tunnel, but we had to test subscale, about 1/3 scale parachutes in that wind tunnel. We tested over 55 different parachute designs. We would do things like take off-the-shelf paintball smoke grenades and set them off to watch the smoke travel around the parachute to try to get an idea of what the flow field was like. Streamline visualization on some of it to, again, try to get an understanding of what the aerodynamics of the parachute would be like. We test a parachute, see how it flew, see how much it moved around the tunnel, see how much drag it generated. Then we'd turn off the wind, parachute would fall on the ground, we'd take a pair of scissors, and we'd start cutting it. Put a hole here, put a hole there, and then we'd turn on the wind, see how it flew, bring it down, try again. We did this over 55 different times. Here's a little snippet of what that video, or what that testing kind of looked like. So here are the winds at about 30 miles an hour. And we just watch the parachute move, we track it, we see how dynamic is the parachute, is the motion, and again, how much force is it generating, how much drag. We use that to hone down to a very specific parachute configuration, one that we felt had a lot of drag and good stability characteristics associated with it. But we also have to do structural testing on the parachute. We couldn't find a way to do that. Again, can't put it in the wind tunnel, can't push it off the back of the plane or anything like that. So we went back to our friends out in the desert, the Navy, and we started working with them on another rocket sled idea, using bigger rockets this time. So this is a picture at night before the setup. You have this funnel, you have a tripod standing over the rocket sled track, and you've got 4 giant solid rocket motors over here. And rather than go into detail, I'll just cut to the video. So this is a video from a test that we conducted earlier this year. We start with a Navy Seahawk helicopter. It's the Navy Blackhawk variation, which picks up our parachute out of a can. This is a fairly large parachute. It's got a lot of volume, even packed. And then there's a rope and a little measurement load plate that we have suspended underneath it. And that parachute and that helicopter, the helicopter will take the parachute to an altitude of about 4,000 feet, just over the track. We release the parachute from the helicopter. It falls out of that bag. The parachute will begin inflating. Again, it's got 4,000 feet of rope and a giant load plate suspended underneath it to help pull it down towards the ground. We watch the parachute inflate very slowly. That straight line is the track beneath it. We have nature do a little safety check for us. This is right before the testers go off. That parachute begins coming further and further towards the ground, and that rope gets shorter and shorter.
50 feet, 30 feet, 20, 10 feet.
Eventually, it latches up to our rocket sled. Rockets ignite. That rocket sled takes off horizontally, and it pulls the parachute towards the ground, and it generates over 100,000 pounds of force. And we routinely take our parachutes to failure to see how strong they are and where they fail, to understand how they fail, and to see if it's something that we can improve easily. This one was designed for a load of 80,000 pounds, went to over 120,000 pounds in this test, before ultimately one of the ropes further down out of the field of view of this camera failed. You can see it in slow motion, and again see how the parachute failed, and if it's an area that we think we need to improve, and if we can improve. Another fun view, this time holding it a little bit longer. So parachute latches up, rockets ignite. And then if the parachute separates from the rocket sled, the rockets take off very quickly. They begin pulling that rope through. There's even a little ant that got woken up and is now running for dear life. So those are some of the structural tests. We also want to see other aspects. We want to see these devices deploy and inflate in a supersonic flow field at several times the speed of sound. We want to see how much drag they produce in the supersonic environment. We want to see how they slow down, how dynamic they are, how stable they are. Do they survive a supersonic inflation? And do they give us the performance that we need subsonically, again, to operate safely at Mars? So this is a complicated diagram. In fact, I'll skip this, and I'll go straight to another video and talk about another test architecture that we had to develop. So we build a test vehicle. Again, looks very similar to a Martian entry vehicle. We put a giant rocket motor on the inside of it. We load it up with technologies. We ship it out to the west coast of Kauai, where there's the Navy's Pacific Missile Range facility. And then, late in the night, the morning before we launch, we hook it up to a gondola. This gondola is at the bottom of a large helium-filled scientific balloon.
Counting. All stations, the three-word hold protocol is now in effect. Only those with proper hold authority are allowed to call a hold on the project net from this point through balloon launch.
This balloon, fully inflated, is 34 million cubic feet in volume. For scale comparison, that's a little bit larger than a large football stadium. So think the Rose Bowl in Pasadena or where the Washington Redskins play, something that's a little bit larger than either one of those. It weighs several thousand pounds, but the balloon itself is made from a very thin material that's even thinner than, say, a garbage bag. We use several thousand pounds of helium to inflate it, and it has to be that large to hoist this full-scale entry vehicle, this 15-foot diameter vehicle that weighs 7,000 pounds itself.
Attention all stations. The test vehicle is go for drop. I repeat, test vehicle is go for drop.
4, 3, 2, 1, drop.
The balloon will carry the test vehicle to an altitude of 120,000 feet, about 4 times higher than a typical jetliner flies. We then release from the balloon, we spin the vehicle up for gyroscopic stability, and we light that large solid rocket motor. This is a Star 48. It's more typically used as the third stage of a Delta II launch vehicle, the rocket that would typically send a spacecraft from Earth orbit to Mars orbit. But here we're going to use this rocket motor to accelerate us from 120,000 to 180,000 feet and get us going from 0 to 4 times the speed of sound. There's the balloon in the background. Once we release, it tears itself, falls down in the Pacific Ocean. We go in and recover it. We don't want to leave that much plastic in the Pacific Ocean. We like to be good stewards of the environment. And that rocket motor will burn for about 70 seconds. There's the Earth, the Pacific Ocean in the background. Once it burns out, we despin, and we get ready to conduct our test. So now we're going the right speed for a Martian entry, and we're in an atmosphere at 180,000 feet, halfway to the edge of space. That is the same thickness as the Martian atmosphere. So we can do our test. We can inflate the SIAD in a fraction of a second. You see how stable the inflation was, how stable the vehicle is after the inflation. Doesn't move around a whole lot. That inflatable decelerator takes us from about Mach 4 down to Mach 3, where we deploy another drag device. This time we shoot a 30-pound pack that's about the density of wood out the back of the vehicle at 200 feet per second, and inside is about a 15-foot diameter ram air inflated drag device that we have to use just to pull the parachute off the back of the vehicle. The parachute itself is 200 pounds of nylon and Kevlar. We try to take that and get it to inflate in a 2,000 mile an hour wind and see what happens. In this case, we find out it doesn't survive that wind very well. It does create some drag, helps slow the vehicle down. The attached inflatable decelerator begins deflating, and all of this comes down to the Pacific Ocean, where our recovery team is waiting to scoop it up and bring it back for analysis. That was a test we did last year as a shakeout for this test architecture to see if we could even conduct these tests, if we could get to the right conditions. But ultimately, it was extremely successful. We had a number of accomplishments, including the largest inflatable decelerator ever tested at supersonic conditions, that 6-meter, nearly 20 feet diameter inflatable decelerator. The largest balloon, that little guy in the lower right-hand corner, that would ever been inflated supersonically at 4.4 meters, nearly 15 feet in diameter. This was the first ever supersonic pilot deployment of a parachute that is using another device to help pull the parachute out. and a supersonic flow field. And it was the largest supersonic parachute that had ever been deployed. But the quantity and the quality of the data, this was perhaps the exciting thing for me as the principal investigator, was the realization that we had been using these devices for 4 decades, but our understanding of them was very little because we didn't have great data sets associated with them. The instrumentation, the cameras, high speed, high resolution, the amount of data that we got, the gigabytes of data, were several orders of magnitude more than we had had in, again, the 40 years of actually using these devices. So we started to get a much better understanding of how they operate. But that was all last year. So what did we do this year? Well, we built 2 more test vehicles. And again, we loaded one of them up with a new parachute design, new technologies, new instrumentation, and we shipped that out to Kauai with some of our engineers, and we did another test. But before we got to that, we actually took that larger device, that 8-meter ram air inflated device, and we got to do some testing on that one as well. So I'll show you some of the rocket sled videos from that. We did deployment tests, not without a wind going, just to see how the side emerged. Was it uniform? Did it go, since this device is much bigger, how quickly could we get it out from the vehicle? We did lots of analysis, computational fluid dynamics to see the flow field around the device to help predict the drag before we actually did the test. Then we integrated it to our rocket sled. We got ready to test. You can really accelerate 40 tons of steel pretty quickly if you got enough rockets. And again, we got to see how these devices inflate. This was something that really relied more on scooping air around it to help pressurize. And that was something that was very new, very experimental for us. But we see those inlets emerge very cleanly, very uniformly, begin to scoop up the air, ingest the air, and help pressurize this device. And here we're going a little over 200 miles an hour. We also see if the device is stable. There's some oscillations going on. We're beginning to understand that the flow field around these inflated structures and how they interact with that flow field is different. We've got some engineers, the 2 engineers in charge of the test and the device watching. One on the left's looking a little skeptical. But they're excited when it works. They were in a room that we couldn't go in. So it was just them and a couple other folks. And we get to have fun with cameras. If you've ever wondered what it would be like to have 40 tons of steel fly over you at 200 miles an hour, now we know. The 2 engineers, another story about that. We were in another room that was adjacent watching the test, and the one on the left who looked very skeptical and got very excited, once it worked, he came out, and the first thing he said was, "I told you it'd work." He was right. But of course, we had the parachute still to test in that new test vehicle that we built, so we shipped that out, and we try again. So this was June of this year. There it is being transported out to the area where it'll attach to the balloon, pushing it out, interfacing it with the balloon. Inflating the balloon. See the large helium tanks on the side.
Release the balloon from the spool.
Once we release for the balloon has to carry up, and it carries over this tower where the where the test vehicle is attached. And the balloon ideally keeps going over, but the wind was so calm this day that we were trying to see if the balloon would carry past so that when we released it, the test vehicle would push off. Background chatter there is the 2 engineers talking to each other, one of them saying, "We don't think it's going any further. In fact, it's starting to come back." And the second one saying, "Release, release, release." Launch it. So it goes to 120,000 feet. Releases. There's the Pacific Ocean. It was such a clear day when we conducted this test that we could actually see the balloon the entire time, and you could see the contrail from the large rocket motor as the vehicle was being accelerated to higher and higher altitudes and faster velocities. There's the balloon beginning to tear. Streaking across the sky. Something different with this test is that right after we spun down, there was a disturbance on the vehicle. Something pitched it, started rocking at fairly high rates and fairly large angles. We're still not positive what it was, but atmospheric scientists sometimes call this region the atmosphere, the ignorosphere, because there's so little that we understand about it. So one of the ideas is that there's these potholes in the sky, pockets of density that we may have hit that pitched the vehicle and disturbed it. But once we inflated the SIAD helped damp those oscillations out considerably. The SIAD worked flawlessly for us again. Inflated, held its shape, and gave us very good aerodynamic performance to help slow the vehicle down. We deployed the Blute at about Mach 3, 3 times the speed of sound, 2,500 miles an hour or so. It worked flawlessly for us. One of the scariest aspects of the entire test was, would this Blute even inflate? It's got ram air inlets on the side, and nobody had gotten previously last year a Blute this large to work in the environment that we were testing in. But it worked flawlessly for us, helped pull the parachute. We took this new parachute design, one that we had structurally strengthened considerably, that we had tested over 120,000 pounds, that we had analyzed and predicted that it should survive loads of in excess of 300,000 pounds. And we saw that it got all the way up to full inflation, right at the moment of full inflation, and then a large tear developed. And once that tear developed, the parachute began shredding. So again, it comes down to the Pacific Ocean. We go and we scoop everything up. Some divers from the Navy Explosive Ordnance Disposal Team. That's the Blute, still inflated on the surface. In fact, that was several miles away. When they finally caught up to it, they realized that it was sailing on the surface of the ocean, that it had stayed inflated, that those little inlets were scooping up the wind, and the wind was just pushing it along at several miles an hour. So what happened to the parachute? Well, we made it a lot stronger, and the areas that we had seen it fail, we changed the shape of it. We used all of our state-of-the-art analysis tools to try to predict the loads and that it would see at full inflation. It said it should be perfectly fine. We tested it using those rocket sleds, and it survived over 120,000 pounds. But what we found out was that in supersonic inflation, those very rapid inflation and the shape and the transients that occur during that rapid inflation, that even though we were only measuring about 80,000 pounds of drag, that the stresses and the forces associated with those inflation were well beyond anything that we could predict and anything that we could test to. And so we start to realize that there's a huge disconnect between how we analyze and how we test our parachutes and how they seem to perform supersonically. If you think about that, I mean, it can be as an engineer who's been spending years trying to develop these things, that can be a very humbling experience when something that you predict to work so well doesn't. But that can also be a very exciting time, right? This is like, navigators of old starting to realize that the Earth isn't flat anymore. It gives you an entirely new world of opportunity to understand, to predict, to analyze. There's so much more that we can learn, that we can test to. And that's really why we're doing these tests. We don't do them just to succeed. This is technology development, right? If everything worked right the first time, then that tells us that we're not pushing the envelope far enough, fast enough, or hard enough. So the fact that we saw the parachute fail, in fact, the 2 parachute failures that we've had in the past 2 years have given us more insight into supersonic parachutes than we've had in the previous 40 years of actually using them. So I want to end the talk with a quote that I think is appropriate for technology development. It's from Theodore Roosevelt. It says, "Far better it is to dare mighty things, to win glorious triumphs, even though checkered by failure, than to rank with those timid spirits who neither enjoy nor suffer much, because they live in the gray twilight that knows neither victory nor defeat." Most of the technologies that we've been developing have worked flawlessly for us. We have further to go to understand the supersonic parachutes, but in those defeats, we will learn more, we will make corrections, and we'll come back, and we'll continue to develop these and get them right. Because these are the technologies that will be critical for the next decades of Mars exploration, looking at the next opportunity of robotic missions and looking all the way out to the horizon for human missions to Mars. So that's my talk. I can take any questions. I think we have, yes.
Tyler Banks, and I'm from Whittier Education Campus.
Hi, Tyler.
And my question is, how long did it take you to make all the parachutes?
The parachutes themselves, months. There's, just the cords that connect the parachute down to the test vehicle. If I take all 96 and I added them up, there's about 3 miles of very small diameter Technora cord that's strong enough to lift a car, but also very small in diameter. The fabric itself, that parachute had nearly 2,000 panels, about this big by this big. Each one of those had to be stitched together, and each one of those had to be stitched to Kevlar reinforcements to provide the structural skeleton of the parachute. So each parachute overall takes months to build, probably 3 to 4 months. Thank you.
Hi, my name is Damien. I'm from Whittier Education Campus. I wanted to know how long does it take for a rover to scan the atmosphere or the surface of Mars?
Well, the rover can only travel so far over Mars. Mars is still a very large planet. It's not quite as big as Earth, but it's still relatively large. And so when it scans the atmosphere, it's really just doing a very local sampling. Something like the Curiosity rover can look up into the sky and, for example, take a picture and look at how much dust is in the atmosphere and use that to predict how thick the atmosphere is. But that measurement can occur in a fraction of a second, and it can take several measurements over the course of its operational lifetime, and then begin to piece those elements together in conjunction with other measurements by spacecraft that we have orbiting Mars to try to get a better understanding of the Martian atmosphere. So it takes years and years to develop that full Martian atmosphere model.
Hi, my name is Kimberly Enamorado, and I'm from Whittier Education Campus. And my question is, if the material from the parachute that you made, is it going to be the same material that they're going to use for the astronauts to go to Mars?
So the parachutes are predominantly made from nylon, like nylon that you would find in your camping tent. Ripstop nylon, very similar to that. A little bit lighter, but similar strength. And Kevlar. The nylon really is just there to provide area. The Kevlar provides most of the structural skeleton of the parachute. And those are the materials that we've been using since the mid-90s on parachutes. Before that, the Viking landers actually used polyester for their parachutes. So we've gotten a little bit more advanced in our materials, but it is likely that we will continue to use nylon and Kevlar or some variant of Kevlar like Technora in our parachutes, even in the coming decades.
My name is Samaya from Whittier Education Campus, and my question is the parachutes an example of how the astronauts are going to land on Mars?
Your question is, are parachutes an example of how astronauts will land on Mars? Parachutes will definitely be used for Mars exploration. Whether we use them to land the humans on the surface of Mars is still to be determined. There are other technology out there that I mentioned. We can try to use rocket fuel. It's nice, it's relatively simple, not particularly efficient from a mass perspective. You know, I can take 200 pounds of nylon and Kevlar and have it generate 100,000 pounds of drag, where I can't get nearly that much deceleration out of 200 pounds of rocket fuel. But because the mass associated with landing humans on the surface of Mars might be so large, you might need too many parachutes. And so it may not be feasible to continue to use parachutes. So parachutes will get us so far. We don't know if it'll get us all the way up to the masses necessary to put humans on the surface of Mars.
Next question is from our online audience.
So the online question is, does a parachute work differently in the Martian atmosphere? Well, than it does in the Earth atmosphere, I'm assuming. If you can replicate things like density and Mach number, then you can replicate generally the performance of the parachute. There are subtle differences. The Martian atmosphere is composed of carbon dioxide. The Earth atmosphere is predominantly nitrogen with a lot of oxygen as well. That creates some subtle differences, but in general, yes, they do behave very similar. I'd say one of the biggest differences is actually how fast the parachute inflates. The speed of sound here at Earth, in Earth's atmosphere, is about 50% faster than it is at Mars. That means that our parachutes inflate about 50% faster here at Earth than they do at Mars. But that's 50% of a fraction of a second. So for example, if I were to take that same size parachute that inflated in 0.6 seconds here at Earth, it would inflate in a little less than 1 second at Mars. It's still incredibly fast to take all of that nylon and Kevlar from a very small volume and get it out 100 feet in diameter.
My name is Kasir Pervez, and I'm from Whittier Education Campus. And my question is that when the rover hit the surface of Mars, did it get damaged?
When the rover hit the surface of Mars, did it get damaged? No. all of the technologies that we used to help land it safely worked flawlessly for us. You know, some people refer to that whole Martian entry sequence as 7 minutes of terror, because that's how long it takes to go from the top of the Martian atmosphere all the way down to the surface. And all of the different things that have to work to land that rover successfully worked for us. The hundreds and hundreds of different events that have to occur at exactly the right time all worked flawlessly for us.
Hello, my name is Savani, and I'm from Whittier Education Campus. How long did it take the rover to get to Mars?
How long did it take the rover to get to Mars? Once it leaves Earth, it takes about 9 months to go from Earth all the way to Mars.
Next question is from our online audience.
In the online question, what kind of stitch do you use to sew the parachute together? Lots of different kinds of stitches. Lots of different kinds of seams, lots of different kinds of joints. It depends on what aspect of the parachute you're talking about. Different types of zigzag stitches, box X's, French fell seams, normal seams, you name it. And depending on the element of the parachute, it's probably got just about any kind of stitch that you can think of.
What was your difference between the PSI when you was testing the probes and stuff on Earth than it was on Mars?
What's the difference in PSI between the Earth testing and what we would use at Mars? Well, when we test at very high altitudes, the atmospheric pressure at Earth is very low, just like it is at Mars. So you don't need a whole lot of pressure. When we were inflating these devices, that 6-meter diameter yellow donut that we inflated, that was inflated to about 3.5 PSI. And that's about as much pressure as you would need at Mars. That big ram air inflated device, that was inflated to a little less than 1 PSI. And it still helped get that shape fully open.
Hi, my name is Ashley. I'm visiting from Georgia. Thank you for your talk.
Thank you.
I had a question about, since the parachutes seem to be ripping at these altitudes, are you guys looking into developing any kind of textiles that could work better at those conditions or anything?
The question is, since the parachute was ripping at these altitudes, are there textiles that we're developing that would work better in those environments? In general, we use the most state-of-the-art textiles that we have. There's lots of trades that you have to make. One of the things that we began learning was nylon, for example, is very elastic. It stretches. When it's stretching because of load, you can pull it to about 20 to 30% its length before it fails. Kevlar, by comparison, is extremely stiff. It will only stretch about 2 to 3%, maybe 4% before it breaks. When you mix the two materials, there's subtleties associated with how the materials interact. When the nylon begins loading, it begins stretching, and it'll take all of the stress, and it will just dump it to the Kevlar. And so if you're not understanding how these materials behave and interact with each other, that's one of the challenges. That was something that we generally had an idea about, but we didn't understand the sensitivity to. When we've looked at other materials that are out there, things like Kevlar and Technora are pretty much the most state-of-the-art in terms of weight per strength of materials that you can use in devices like this. Nylon for the broadcloth. There are alternatives out there, but generally you have to make sacrifices in other areas. Maybe they don't survive some of the temperatures as well. Maybe they have other things that they don't respond to. For example, the cold environment from the transit from Earth to Mars. Maybe they begin to brittle. So in general, we think that we've got the right materials. It's mixing them in the right combination that we're still wrestling with.
Next up is an online question.
Online question, is it disappointing to watch the parachute shred after so much work went into it? As I said, it can be a very humbling experience. But I think the initial disappointment gets replaced with the realization that you're going to learn from that. You're going to have to pick yourself up, figure out why it failed, and through that understanding, then begin to apply that. That's something that it's knowledge that we haven't had. And so that's an exciting aspect, is that you are beginning to push the frontiers. You're, again, on the very edge, cutting edge of the envelope for these technologies. And you're getting the know-how to push that envelope and to get these things to eventually work. So there is an element of disappointment, but there's also an element of excitement because you're learning something new, something that nobody else has seen before. And that means that, you're doing the right job.
Hey, my name is Tom from Whittier Education Campus, and I was going to ask, how does the aerodynamics of the parachute affect the drag?
How do the aerodynamics of the parachute affect the drag? Well, it depends on the environment that you're in. So supersonically, right, the parachute is inflating behind this blunt body. This blunt body is screaming through the atmosphere. It's essentially punching a hole in the atmosphere. And in that hole, all of the air is rushing around it. And it's a very turbulent, very chaotic environment. And so that's what the parachute's beginning to inflate in. And how it interacts, well, there's a tight coupling because the shape of the parachute determines the flow field around it, and the flow field in front of it determines the shape of the parachute. So there's this interaction that goes on, and because the environment in front of it's so turbulent, it creates a very turbulent acting parachute. So the aerodynamics, things like how much pressure is inside, how stable is that pressure distribution, all affect the shape. And then the drag of the parachute can fluctuate. At high Mach numbers, it can be a fraction, 1/10 the amount of drag it generates at Mach 3 that it would at, say, something less than Mach 1, 100 miles an hour. So the difference between drag at 3,000 miles an hour and 100 miles an hour can be an order of magnitude. It can be very, very large. Great question.
My name is Jelani Shepard from Woody Education Campus. My question is, how does the rover and parachutes land in the right destination on Mars?
How does the rover land at more destinations on Mars?
How do you guys know if it's going to land in the right destination?
How do we know that it's going to land in the right destination? Well, it's a very challenging problem. You're trying to go, millions and millions of miles from Earth to Mars. You're trying to enter the Martian atmosphere at a very small window, say, a few kilometers in size, and then you're trying to put that rover down on a relatively small area. Back when we landed the Viking landers, that area was about 160 to 200 kilometers long. We actually didn't have a great idea. We knew that there was a lot of uncertainty in terms of how much drag, how thick the atmosphere was, how the vehicle would fly. If there are winds, would they begin to push the vehicle while it was on the parachute and drift it off course? From Viking to 200 kilometers of Viking, when we landed Curiosity, we got that down to less than 10 kilometers. We'd actually shrunk our uncertainty down to about 10 kilometers. So there's still some uncertainty, about 6 miles or so, in terms of where it will land. But we've been able to make some significant improvements on that.
I wanted to know, how long did it take to make the rover?
How long did it take to make the rover? Years and years. We're planning a rover very similar to that will launch in 2020. And the engineering, the development of that is actually going on today, 5 years ahead of schedule. All of the design, the testing, the analysis, that all takes years to conduct, and then actually fabricating the materials that put it together, that takes years. And then finally assembling it generally will take over the course of a year or so, doing the integration, the assembly, and all of the testing or so.
Hi, I'm David O'Brien, visiting for Chicago area. I was wondering if the CFD simulations you had, were they able to predict some sort of possibility, the probability of the tearing of the parachute, and how you might use the tearing event to help shape your future CFD simulations?
The question is, did our computational fluid dynamics, our computer models of the aerodynamics around the parachute, did those predict anything associated with the tearing on the parachute? And then the second part was, could we use them to predict future, make modifications? In general, the answer to the first question is no, not really. We've used pretty much the state-of-the-art, the same tools that we've used successfully, but when we begin applying them to much larger parachutes, inflated at much faster velocities, we find that they're not able to adequately predict all of the stresses, pressures, forces that are going on inside the canopy. So there's a deficit there. We're in the process of taking the data that we're generating from these tests and using that to improve our modeling capabilities, but we're not there yet. And I think that's all for questions.
It is. We would like to thank Dr. Ian Clark for coming to the museum today and presenting the findings that they've uncovered so far. We'd also like to thank our sponsor, Boeing. Thank those of you that are watching online, NASA TV, and those of you in the audience. Thank you for being here today. Thanks, Ian.